Okay, so today I'm going to talk about return flow, and I think it's pretty likely that some of the people in this room know a lot more about return flow than I do. But for everyone who doesn't, what I do want you to take away from this presentation is an understanding of what return flow is, why return flow is so important to be able to measure and important for hydrology in general, and also what we're doing here that's a little bit, maybe a little bit different in Wyoming to measure return flow. So the first slide I have up here with untangling the water budget shows a picture of our field site in DuBois, Wyoming. So if you're familiar with that, sort of at the north end of the Wind River Range. And I just want to point out the people that were working on this project with me. Ginger and Scott are really the people with the ideas here, and then me and Niels are of course the ones actually doing the work, and I'm sort of tucked there in the middle. You get to hear me talk about it. So I'll start out by just saying a little bit about what return flow is. So the main sort of point is if we take water out of the creek and use it for irrigation, how much of that water gets back into the creek ultimately. So the example here I'm showing on the, I'm showing here is this is the whole Spence Moriarty Wildlife Habitat Management Area, and basically all of the green part is the watershed that we're concerned with, and the creek runs right down the middle. So the idea here is we divert water, or not we, but water is diverted from the creek up here at the upstream area. It's sent along a ditch, the solid red arrows, and then flood irrigation is used to pass that water across the field. Ultimately, some of that water is going to make it back into the stream downstream, and this is the return flow. So the question is not only how much water returns, but through what pathways, and that's a really nice basic science question in terms of hydrology. I'm sorry to this side of the room that I can't use the pointer on both screens at once, but look over here. So the photo on the right here is the ditch. So this is the water that's been taken out of the creek, and then this is just a gate. And then you can just see one of the little pipe sticking up that would be a flood irrigation pipe that actually runs horizontally along this. So let's take a different sort of perspective on this. So we talked about in general what's return flow, but thinking about this in a cross section. So this is a hill slope going from the ditch at the top all the way down to the creek at the bottom. This is Bear Creek, it's called. And so in cross section we have our diversion ditch, some irrigation, and then we have a lot of arrows. And all of these arrows are trying to sort of get at that question, where is the water going before it gets back to the stream? So of course one of the main reasons that we're doing, or that irrigation is being done, is for the consumptive use. The point is to grow something using this irrigated water, so that's the consumptive use, what water is being simply taken up by the crop. The evapotranspiration component, this is water that's getting back to the atmosphere, basically that's not going to end up as return flow. There's some surface runoff, so this is called surface runoff or overland flow. Just whatever water is flowing directly over the ground surface and may make it all the way back to the creek as overland flow. A lot of water, though, will infiltrate, and this is where we get to sort of the subsurface component, which is a little bit more difficult to study because this is sort of out of our direct view. There's going to be some component of the water that is actually stored on a longer time scale than we're calculating return flow. So this is also sort of leaving the system in a way, at least on short time scales. And then we have a couple really important arrows. The vadose zone flow, or unsaturated zone flow, the VZ flow one here. So this is water flowing through the unsaturated zone, maybe making it back out onto the slope and then continuing as overland flow, or maybe making it directly into the stream. Of course, the other one is saturated zone flow or groundwater flow. And so how do we actually measure this? Well, what we actually want to do is a water budget. So this is not conceptually that complicated. We measure what's diverted. Some of it's used in irrigation, so some of it's lost to groundwater, some of it's lost to the evapotranspiration component, and some of it's stored for a longer amount of time. And then we measure the stream flow at the bottom of the watershed. And this should add up to 100%. If we know where all the water went, then we should just get 100% at the end. But what it turns out is that all of these arrows are extremely difficult to measure. There are some that you could sort of think are a little bit easier to measure, but everything has error bars, and in the end, this rarely adds up to 100%. So this is one of our main challenges, is getting this to add up to 100%, because then we can actually figure out what is the return flow component. So what are we doing different? Well, our goals are to reduce the uncertainties, to shrink those error bars on at least a few of these pathways. We want to reveal heterogeneity, so we want to look at how the hydrologic system is variable spatially across our watershed, and not just make these broad-scale assumptions and upscaling. The other thing that we want to do is illuminate these highly temporal hydrologic processes. And so in order to achieve all of these goals, we're using some geophysics. Obviously, that's why I'm up here, and I'm a geophysicist. We're using some slightly more conventional streamflow type measurements, and then we're also using some pretty novel measurements of our atmospheric water component. And so I'll talk about each of those things in the next few slides. So one of the obviously most important things that we can do is measure how much water is moving through the creek. This is going to tell us upstream and downstream, between the diversion, how much water is getting taken out of the system and is effectively in the system at the end of at the bottom of the watershed here. So on the right here, I'm just showing you again the sort of smaller map of that Spencer Abbey Wilderness Habitat Management Area. Flow is going from top to bottom, and we have two stilling wells, and a stilling well is just a place where you can put a pressure transducer so you can measure how high the creek level is at that point. So the upstream stilling well is called Bear 4, it's in black, and the brown, and the downstream one in red. And by recording the level of the stream across throughout the season, and then developing these rating curves, and Scott actually showed a picture of one of those rating curves in the last presentation where we relate water flow with the stream heights, then you can gauge, based on just your stream height measurement, how much water is flowing through that cross-section of the stream through time. So we do that in a bunch of places. Actually, Scott also showed the sort of more complete map with all of the sensor locations. I just wanted to show you the ones that I'm giving you data from. But these are two different stilling wells here along the creek, and then what we get from that is a hydrograph, right? So we get discharge. This is in non-metric units, so I don't know what it means, cubic feet per second, but that's probably cubic meters per second. And we get discharge as a function of time. So this is the 2014 growing season. And not surprisingly, early in the season, what we see is that the downstream gauge point that has the larger contributing area of the watershed has a larger amount of water. It has a higher flow through it. Simply because the upstream point doesn't have as much of the catchment to contribute water to it. As we go through the season, you get some interesting anomalies. One thing that we know is that the site gets very, very little rain during the year. It has some snow on it during the winter, but during the temperate season or the warmer seasons, it doesn't really get much rain. So bumps like this are actually probably just precipitation events that are happening much higher up in the alpine watersheds, way up here. And another interesting thing that we see on these hydrographs is that the position of the upstream and downstream flow flips. So what we see is that the red line, which is actually downstream, has less flow than the upstream line. And this is a little bit confusing, and there's a bunch of things that you could attribute this to. I'm going to sort of highlight two possible ones. You could have groundwater loss through the stream beds. We were talking before about groundwater surface water interaction. It could be that this becomes a losing stream later in the season. Or it could be something like evaporation. I don't know if that has quite enough to account for all the water that's lost there. But you do see these interesting patterns by getting really high temporal sampling time data sets. Oh, weird. Okay. So the atmospheric component. This is where we sort of start to bring these novel measurement methods into the picture. So on the right here, this is actually conventional. This is the Met station. It has your wind speed and direction and net radiation and temperature measurements on it. But this is sort of the cool one, sort of hiding out there in the trees. This is called a scintillometer. And what this instrument does is at high time resolution again. It can very carefully measure basically the heat balance over some transect of the irrigated field. And ultimately, this is going to be used to calculate evapotranspiration at a site-specific scale. And this is really important because right now, the only way we can do some of these calculations is with these statewide averages. So this is an example of an instrument where, by having this at the site, we can really do a better job of closing the water budget without using some sort of back-of-the-envelope numbers. So of course, here's one of the sort of key goal data sets to come away with is consumptive use. So here it is. How much water is actually being used in the plants that are grown. And one thing you'll immediately notice from both of these graphs is they have this stair-step pattern to them. And that's not actually, that's basically noise to us. That's an effect of using the statewide average estimates that go into these calculations. And so this is from, oops, go back. This graph is from 2014, obviously. So we're getting the 2015 data now that has a scintillometer, and we should be able to make these consumptive use graphs look much better and more accurate by having integrated things like the scintillometer. So here's the video that Scott was going to show before, but I get the glory, I guess. So the idea here is that we use electrical resistivity tomography, where we inject some current in the ground and look at how that response changes as a function of saturation. And so on this slight hill slope here, we have an irrigation pipe at the very top. And what we're going to do is irrigate starting at time 0, and then watch over 4 hours how the subsurface changes. And so I think I have to. And so the things we can realize from this are really high time resolution imaging of that wetting front as it moves downward. We can also image some things like these preferential pathways that show areas where the water is getting into the ground faster. And so this is an extremely powerful tool for being able to get at that question: where is the water flowing in the vadose zone? Where is water flowing in the saturated zone in some cases? So this is going to be a really important part of tracking some of that water as it moves to the subsurface. This is only done over a few hours. Obviously, you could set this up for longer amounts of time to get a sense for how this is variable, depending on different starting conditions. Another thing we're doing, again with geophysics here, so one of the questions is how heterogeneous is the aquifer here? So how much heterogeneity is there in how much water you can store in the subsurface? And so for this part of the experiment, we're using a geophysical method called surface nuclear magnetic resonance, or surface NMR. And without getting into the gory details here, the main point is that this is the only geophysical method that is going to directly detect water for us. So that means it's unambiguously a measurement of how much water is stored in that aquifer. And so we can go around our entire watershed area and make many of these measurements to characterize how much water gets stored in this aquifer, at least at certain points in time. This is not a time-lapse measurement, so there's no animation here, but I'll talk you through this a little bit. On both of these graphs, the depth is on the y-axis and the water content is on the x-axis. Do be careful, this x-axis has a different number of units on it. And so what we're looking at here is basically an aquifer that is confined to the top 10 meters, and below that, there's really no significant storage. And it's not totally clear yet whether that's because this is bedrock or whether it's just because there's some sort of material that's precluding the water from going deeper. But what we can tell is in at least some areas of our site, we have storage on the order of 15 or 20% porosity. If we go to other areas, this is probably only about 500 meters away from this one, what we see is much less storage. And so the story here is that there is a significant amount of heterogeneity in water storage in the groundwater across this site. This one is only about 2%. Okay, so why is this important? So across the U.S., what we're looking at is 37% of water is being used for crop irrigation. That's exactly what we're talking about with consumptive use. So using water from the creek in order to grow crops. So that's actually quite a big number. And sort of even bigger number is approaching 90% potentially of consumptive water use overall is attributed to agriculture. So this is a really huge number. Agricultural water use is something that you need to fully understand how it works in order to manage it properly. And specifically, so our field site here, we're using flood irrigation, and so this accounts for about 26 million acres, at least in 2005. And so this has the possibility to be really broadly applicable. And so the main point, to wrap it up, is that better understanding of these processes that govern return flow is going to really be important for better water management. And so the last slide here, I just want to give you an outlook and say that, so this is really only the second field season of hydrologic data that we have right now, so we don't have all of the water budget tied up at 100% yet, but we can see the writing is there that we have these high resolution time and space data sets are going to be completely transformative to our ability to close this water budget and get it the return flow. So with that, I think I've used my time mostly, so I can take a question. All right. If you have any questions, I'll take them. Oh, yeah, sorry.
What was the landscape like on the Cheaterman site? You had an NMR that was issued for.
Yeah, so it's basically all the same. It's basically it's this grass that they grow. It's all basically the same-ish slope and the same type of planted grass that they kind of harvest. So you can't really tell the difference from topography or vegetation community or anything. There's just a big difference in the amount of water stored.
Awesome. Do you know what the difference is in terms of the contributing area between what's delineated in Bear 1 versus Bear 4?
The difference in the contributing area, I don't know those numbers directly, but Niels, Ginger?
B.
B.
You know.
I didn't see B.
I know.
That's why, you just didn't want to answer questions.
Right. Sorry. It's
Sorry.
not all that significant, just in terms of the topography, in terms of the contributing area. Maybe 3% change in total area contributed between the upper and the lower. That's an approximation.